Here's the next lab. I got 100 grams hanging off the pulley, string going up to the cart. I've got a wooden ramp, rubber band to the top of the cart. We're going to take a steel ball and we're going to put it on top of the wood. It's got a little groove to sit in. Now, when I let go of this, I get the blocks out of the way. This is going to take off and go down the runway, and we want the ball to stay right where it is on the wood. So if I let go, it comes down the hill. If the cart goes too fast, it'll shoot up. I want it to stay right here as the whole thing goes down the track. We need the angle of the wooden track. So from the metal to the top of the wood, I get about 7.5 centimeters. Near the front of the cart, I'm getting about 5.8. The horizontal distance between those measurements was 15 centimeters. From those measurements, you should be able to get the angle of the incline. I'll get some masses. I'm putting the tray on here, tearing it. The metal ball is 66.9 grams. The cart with a wooden track on it is 566.6 grams. Let's see what happens if I release it just the way it is. Well, the cart took off too fast and the ball rolled uphill a little. Let's see what happens if I put some more masses on the cart to slow it down. Well, now I have 300 more grams on the cart. Let's see what happens now. Well, the ball started to roll down the ramp. So what mass would I have to have on this cart so that the ball will stay right where it is on the ramp as it goes down the track? So we're going to try to find the mass to put on the cart so the ball won't roll. We have 100 grams hanging off here. The cart is 566.3 grams, including the wood, and the ball is 66.9 grams. So from the track, I measured up to the top of the wood at 7.5 centimeters, from the track to the top of the wood, 5.8 centimeters, with a distance of 15 centimeters between these measurements. So we have opposite over adjacent would be equal to tangent theta, giving us 6.47 degrees. Free body diagram is in order. We draw on the weight, and instinctively, everybody is going to want to break this up into components. We see an inclined plane, and we know what to do with an inclined plane. We know the theta goes here, and the component perpendicular to the plane would be canceled by the normal force. And the component parallel to the plane would therefore be the resultant, and that would be the force acting on the ball, making it go down the ramp. There's only one problem with this idea. The ball doesn't go down the ramp. Does the ball actually move? Well, a lot of people say it doesn't move because we want it to stay in place on the ramp. But the ramp is moving. So the ball actually does move horizontally. This is not the proper resultant. These are the only two forces acting on the ball. But instead of breaking up the weight vector, we're going to break up the normal force vector. Because we know the ball does not rise or fall, the y component of that normal force equals the weight. And it's the x component of the normal force that makes the ball move horizontally. Because we know the ball is moving sideways, we know this must be the resultant force acting on the ball. Theta goes here. The y component of the normal force must equal mg. And the x component of the normal force must equal the mass of the ball times the acceleration of the ball. That acceleration is the acceleration of the entire system sideways. I have a right triangle formed with these components. What's the relationship? Opposite over adjacent equals tangent theta. G tan theta is the acceleration of the system. If we analyze the entire system, we can say that the sum of the external forces, that would just be this force, is equal to the mass of the system, and that would be the mass of all of these, times the acceleration. We now know what the acceleration is. It's g tan theta. Plugging in our values, we have 0.98 newtons for this force, 0.1 kilograms for this mass added to the mass of the cart over here with everything, all times g tan theta is 1.1107 meters per second squared. And I get 782.4 grams for everything over here. So that's the mass of the cart, the mass of the ball, and the unknown mass we have to put on that cart to get to this value. I get 149 grams. Let's see if it works. Well, we last tried with 300 grams. Let's see how we do with 150 grams. Not bad, but it rolled down just a little. We're going to 100 grams. Let's see what happens. Oh, that's perfect. So we got it to work best with just adding 100 grams instead of 150 grams. Does that make sense? There's a little bit of friction in the system. I needed the cart to go a little faster. So by reducing this mass, the cart accelerated a little quicker and the ball stayed in place on the wood. Let's see if you can generalize things a bit. If you were given the mass of this part of the equipment, that's the ball, the wood, and the cart, and you were given the angle of that wooden ramp, would you be able to find that mass so the ball won't roll? When you come up with a formula, you gotta test it at extremes. I know some of you are still wondering what was wrong with this diagram. Well, I'm telling you, the ball did not roll down the hill. The acceleration is not in this direction. But if you have a problem where the ball is going down the hill, then yeah, that's perfectly fine to use. If you apply mg sine theta and you work out your equation for this problem, when you test it at extremes, you're going to see it won't work. But what's interesting is that if the angle is small, sine theta is approximately equal to tangent theta. They get real close for a small angle, and that's what we have, a small angle. So even if you use sine theta at our experimental data, you're going to get a reasonably close answer. But when you test it at extremes, it's going to break down. Well, you might be thinking this was really unusual. We never broke up the normal force into components and made them look like this. But I'm telling you, you did. It just wasn't the normal force. Get rid of the plane, make a little room, and put in a string. Yeah, we did this, lab. Take a weight, put it on a string, and whirl it around in a conical pendulum. We did this, lab, last year. That's the diagram we used, because the centripetal acceleration was horizontal. We didn't want to break up the weight. We wanted to break up the tension in the string. Now you can go make up your own conical pendulum lab to test this diagram. It's going to involve tangent theta, not sine theta. The angle won't be small, and boy, will you see a difference if you use sine theta. It won't work. Good luck, everybody.